Over the next few videos, we're going to take a look at the different aero parts on an F1 car and understand just what the heck they're doing, so that next time you're watching FP1 and they start talking about new dynamic phalanges on the underside interior of the Ferrari, you might actually know what the hell they're talking about. F1 cars are, unsurprisingly, quite advanced, aerodynamically speaking, but if we can start to understand just a few basic principles of how air works, and why and how engineering wizards like Adrian Newey are shaping the airflow around their car, we can start to appreciate when new parts come onto cars and how they may be good or bad for the performance of the car. But before we dive into looking at Venetian blinds, louvres, wakes, ground effect, gurney flaps, tip vortices, dirty air, and the fact that the 2022 cars look like a goddamn spaceship, and I love it, we need to understand one simple thing. Welcome to F1 Explained. Like and subscribe, you know how it works. Let's talk about pressure. To talk about pressure, we need three simple equations and one basic principle. Those equations are these. As you can see, they're really... That's not simple at all. Well, actually, just hang on a second. They're not as bad as they first seem. Let's break these down real quick so we can see what's going on. So that first one, P equals F over A. Little p is pressure, the thing we're talking about. F is force, and A is surface area. This one is important because we want a force, downforce, acting on our car to help it generate grip. So if we swap this around a little bit, we can see that if we have big pressure and a big surface area, then we get big force, and big force is good. So if we know that we want a big pressure around our car, or more specifically, a big difference in pressure between the highest part and the lowest part, well then how do we change the pressure of the air? You can't just squeeze the air, or can you? So, little p over rho plus v squared equals k. What? Well, that little p is pressure again. We know how that works, that's all good. This little Greek thing underneath is rho, which stands for the density of the fluid. Basically, how much air we have in our air. If you squish your air down, you've got the same mass, but in a lower volume, which gives us a higher density. And that's actually what this third equation here shows us. Density, rho, equals mass over volume. You put more stuff in the same amount of space, it's more dense, who would have thought? So, back to our second equation, this v is actually a little v, which means it is velocity, not volume, effectively the speed of our fluid. And actually this is squared, which means that it's speed times speed, which means that actually a small increase in the velocity of our air can have quite a big effect on the overall pressure difference that we get. And then finally, K. K is just a constant. What is the constant? I don't know. It's different every time we look at this. But in each scenario, whether we're looking at one wing or one diffuser, K is always the same thing. It cannot change. This means that if we do change one thing on the left-hand side of this equation, be it speed or density, then something else on the left also has to change to keep everything balanced. If we speed up our fluid, then we can see that the overall number on the left-hand side of this gets too big to be K, and so something else has to get smaller. And also at the same time, if we decrease our density, we also have to decrease our pressure to stop this fraction getting too top heavy and toppling everything over. And that's it. Those are our equations. Simple. Well, I don't know if simple is the right word, but hopefully you start to understand what we're talking about. I did also say that there was one basic principle that we have to understand to know why air does what it does. And that principle is that air always wants to move from somewhere high pressure to somewhere low pressure. Always. No exceptions. Air likes to be balanced and level. It wants everything to be the same. So if you've got a pressure difference, the air will try and move between them. And the bigger that difference is, the faster that air is going to move between them to try and make everything even once again. Which is why I said in our first equation that force is actually the pressure difference times surface area. If we can create a high pressure area, then that's good because we'll get some force as the air tries to go back from there to a place of normal room temperature pressure. Cool. But if we can pair a high pressure area with a really low pressure area, like a vacuum, then we get a much stronger force, as the air really wants to get down between the two to balance everything out. And that's what we really want on an F1 car. Now, I don't have any kind of equation or anything to show how or why air moves as it does between high pressure and low pressure, but I do have balls. That was a bad idea. Oh no, stop. There's too many balls. Yeah, nice one, Sam. Just tear the bag open in the middle of the room. Genius. Oh, they're everywhere! I think that's all of them. So, as I was saying, air always moves to fill the space it's in as evenly as possible. Now, you may have noticed these table tennis balls aren't made of air. They're in fact made of balls. But if we have enough of them, they kind of start to act like a fluid. So we can start to talk about some of the ways that we can shape air to generate the pressure we want. So firstly, if we just put something into the air, let's imagine that this is a lovely piece of carbon fiber from an F1 car. But we don't move it around or put any weird angles in it or do anything like that. Does it generate any force? Well, no. Everything's completely balanced, the pressure is the same on all sides of it, so nothing happens. However, if we do have an imbalance of the pressure from one side of this thing to the other, well, the air doesn't like this at all. The air wants to get rid of this as quickly as possible. Currently, we have lots of balls up here, so this is high pressure, and almost none down here, so this is low pressure. The air wants to make everything even again, so it pushes the piece of the car down to try and balance the two sides so that the pressure is the same. This push is the force, and as it's going downwards, we call it downforce. So if we want to have downforce acting on our car, we can see that we need to make high pressure above different parts of it and low pressure below them. And so, what are some things we can do to start to try and change the pressure around this thing? Well, the first thing we can do is start to use surfaces at an angle to the direction of travel through the air. As you can see, when this piece of a car at an angle moves through the air, it bunches up some of the air on one side and leaves a big old hole on the other side. Just like before, this bunched up area is now high pressure and this big void underneath is low pressure. And so congratulations, you just made a wing, baby. Now, this is a massive oversimplification of what's actually happening around the wing. It's basically correct, but there's all other intricate details as to why the air moves as it does. We'll come onto that in a later video, but for now, you get the general idea. High pressure, low pressure, good. The second important thing we can do to control pressure is to create vortexes. If we can get a concentrated bit of air spinning fast enough, like a little hurricane, this actually changes the pressure. The air right through the middle of this vortex is having to move pretty fast to spin right around the center, and as we saw before, if the air moves faster, the pressure drops. So now we have a nice controlled beam of low pressure air moving in a pretty controlled way wherever we create this vortex. And finally, if we try and shoot our air through a nice narrow gap, then suddenly we have to get loads of bits of air through a very small space. The only way to get all this stuff through this gap at the same rate it was traveling before is for the air to speed up a lot. And again, as we know, fast air means low pressure, which can be very, very useful. This is called the Venturi effect, and we'll talk about this more when we come on to talk about flaws and diffusers on cars in a few videos time. And that's basically it. 3 things, that's all you have to know. In the next few videos, we're going to start to look at how these 3 ways of controlling pressure can be used on an F1 car, or any car for that matter, and specifically what parts engineers make to control air exactly how they want it, which should start to explain why an F1 car looks like it does. Join me to see me play with my balls once more, and in the process, start to understand the aerodynamics of an F1 car a little bit better. Make sure you like this video, subscribe so you don't miss the next one, and until next time, stay safe, and I'll see you guys later.